Okay, I think I can start. Hello, this talk is about Introduction to Based Rollups and Preconfirmations. My name is Lin Oshitani. I'm from Nethermind Research. Okay, so in this talk, I will go over based rollups and preconfirmations, what they are. I'll give a quick intro. And then I will talk about our Taiko preconfirmation POC work to give like one example of an implementation of a based preconfirmation solution. So before starting, let's think about what are rollups exactly. So rollups is a technology that scales Ethereum by posting transaction data to L1, but executing them in L2. So by not executing them in L1, you get the scale. So in other words, you can think of it, rollups, as this. So you put L1 blocks, the L1 blocks contains the L1 blocks, L2 blocks like this. So in the L1 block, you have a bunch of these L2 blocks within them. So the big question in rollups becomes, how do we build these L2 blocks? And how we build the blocks is like a fundamental question in Ethereum research, so it's only natural that it's being asked in the L2 context too. Okay, so like, let's see how most rollups today work. So most rollups use centralized sequencer. What they are is basically the user will send their transactions to a centralized sequencer like this. And then the centralized sequencer will sequence the L2 transactions and then eventually build a bunch of L2 blocks and then submit the L2 blocks to the L1 block building pipeline. And eventually these L2 blocks will be included in the L1 block like this. And like centralized sequencers are very nice. Most notably, they can provide preconfirmations. So what are preconfirmations? Okay, so preconfirmation, let's think of this. Like this user is submitting a transaction C to a centralized sequencer. Now what this centralized sequencer can do is that they can provide a preconfirmation. And what they're saying is that it's saying that I will promise you, so like you send transaction C to the centralized sequencer, the centralized sequencer will immediately return this preconfirmation. And the user, by looking at this preconfirmation, they can know exactly what the state of, or what the result of their L2 transaction will be ahead of time. And then some time passes, and then eventually the centralized sequencer will actually post this L2 block to the L1. And in this case, they're like properly like holding the promise. But the key thing here is that the user did not have to wait until this L2 block to be posted to L1 to know the result because of preconfirmations. Okay, centralized sequencers are nice because they can provide fast UX. However, they are centralized. You have this like single point of failure in the whole system. So that is not great. So the big question here is, how do we decentralize the centralized sequencer? And this brings us to the idea of based rollups. Okay, so the idea of based rollups is this. Let's use the L1 block building pipeline to sequence not only the L1 transactions, but also the L2 transactions. So now and construct an L1 block that also contains these L2 blocks. Okay, so let's L1 block building pipeline. So the user sends their transaction out to the mempool, and then what we call searchers will like bundle these transactions. So for example, if you have a DEX trade, the searcher will insert an arbitrage transaction right after it and construct what's called a bundle. And then these bundles are sent to the builder. And then the builder will collect all these bundles and then construct a block. And notice that they're worth this much. And then they're all going to send bids to the proposer. And the proposer is going to select the highest valued block and then propose it. Used not only for the L1 transactions that are like used blue here, it's also used for the L2 transactions that are used in the red here. Okay, based rollups have very nice properties. Like first, we inherit the L1 censorship. All we have is the L1 actors. So we inherit the L1 security. Another nice thing is that we can get L1 composability. This is because L1 and L2 transactions are sequenced by the same entity. So this builder part, this builder is constructing L2 and provide like composability guarantees. So based rollups are very nice. However, they're slow. So because we need to wait the L1 slot times for any form of confirmation, so like the user, to know what the result of the transaction is, they have to wait until the actual L1 block is built, then they look at the L2 blocks within the L1 block and know what the result of their transaction is. But this takes a lot of time because you have to wait until the L1 slot times. So a big question here is, can we provide pre-confirmations in this based setup? And one thing to notice here is, okay, can the builder provide pre-confirmations? And the answer is no. The builder cannot provide pre-confirmation because they do not know whether they're going to win the auction in the end. Because the proposer is the one who's going to run the auction and choose the winning block. So the builder is not sure. Is that the proposer does have the monopoly sequence right because they are the one who's doing the final sign-off of this L1 block. So they're choosing what L1 block is going to be published, and they have the final say on that. So they do have monopoly sequence right, and they can provide pre-confirmations. So the idea-based pre-confirmation comes from this insight. And the idea here is that let the L1 proposers opt to provide pre-confirmations. So now, like, you have the L1, like, same old block building pipeline, but for the L2 transactions, you can say that, hey, the proposer, let's have the proposer, like, collect these L2 transactions and provide pre-confirmations. And then they construct the final block. Okay, so like this is how base pre-confirmations work. And here, let me give you a specific example or implementation that we are doing at Nethermind in collaboration with Tycho. Tycho is a based rollup. And at Nethermind, is this. So during the proposer's slot time, the L1 proposer will construct L2 blocks from the L2 mempool and every 3 seconds and publish them. So the idea here is that this blue part, it's still running every 12 seconds, so the L1 block's slot time. But the red part, this pre-conf part, every 3 seconds, the proposer will collect a bunch of transactions and then pre-confirm them. And then in the end, like, it's both of the L2 block transaction and L1 blocks is combined and it's built. The L1 block is built. Okay, so let's get into a little more detail. So the sequence diagram that illustrates how our Tycho POC works. And okay, the first thing here to note is this AVS node that I write here. This is a sidecar running alongside the L1 proposers. And this sidecar will be responsible for the pre-confirmation duties, such as registering to be a pre-conf, doing the pre-conf publication, etc. This the AVS node or the L1 proposer will check whether they're registered and whether they're like the next going to be repeated many times. So this until here, until like this part. And this part is going to be repeated every 3 seconds during the 12-second window. And what's going to happen is that the users are going to send a bunch of transactions to the Tycho network, the Tycho P2P. The Tycho has an L2 specific P2P for their mempool. And then the AVS node, every 3 seconds, will L2 block, and then publish the signed L2 block to the Tycho network. And then anyone who's listening to this P2P, they can actually execute because without waiting 12 seconds, the user is able to know what the proposer is committing to. Yes. Okay, a little more in detail. Like, so like what is actually published here? What's published here is this. It's pre-confirmation. First, we have the pre-confirmation header and a transaction list. And the pre-confirmation header, what it contains is a block ID, chain ID, and a transaction list hash. This is the most important part. This is saying that, hey, I, as a pre-confirmer, I'm going to pre-confirm these transaction lists. So I'm going to, like, okay, now, like, later on in the sequence, okay, yeah, then, like, and then, like, one very important thing here is that, okay, what if the submitted L2 blocks here contradict what was pre-confirmed here, right? Because, like, pre-confirmations only work if these two are actually the same. So if they're not the same, we're in trouble because, like, the user trusted the pre-confirmer that these are the transactions are going to be eventually included. What if they're not included? So for that, we need slashing. And for slashing is also done like automatically by the AVS nodes. And the idea here is like what if these signed L2 blocks, they mismatch the subletted L2 blocks? Okay, so here's like some like pseudocode for like how this could work. And the important thing here is like, okay, in the L1 contract, we keep track of what was actually submitted to the actually like mapping to. So like what are the transaction hashes that were proposed to L1 basically? And then we have this prove incorrect preconfirmation thing that will like detect whether like the preconfirmation header and actually submitted L2 block, different things between the preconf L2 block and the submitted L2 block. So like implementation-wise, the most important part is here. You're just checking that what was posted, actually posted to L1, if it mismatches the header that was actually pre-confirmed. And whether it was pre-confirmed by the pre-confirmer, like we check the signature. So pre-confirmation space. So and one thing is what I call pre-confirmation PBS. Okay, so like what we looked at, the POC implementation and what we explained so far is like this setup. Like the user submits the transaction directly to the proposer. The proposer locally builds the L2 blocks and pre-confirms them. But the proposer may eventually want to outsource the pre-confirmation duty to external. So we might want a pre-confirmation PBS because like right now the proposer is building by themselves, they want to outsource the pre-confirmation duties. Okay, how can this happen? Like one way maybe to like have a gateway, what we call, to fully delegate this gateway guy, this will do the pre-confirmation duty instead of me. And then you'll delegate ahead of your slot to this like specific gateway. And the gateway to PBS. So like what I explained for the L1 here, you can have a L2 specific one, but like have the L2 specific one run in more frequently. So the red part in this diagram, it can run every 3 seconds, while the L1 part, the bottom part, the blue part, can run every 12 seconds. And then you can provide L2 pre-confirmation in this that we had for the base rollups. Run this whole thing every 3 seconds. And this way you can get both L1 and L2 pre-confirmations. And thanks to that, you can also get like good composability guarantees. Okay, that's all. And here are some references on our work on pre-confirmations. And yeah, thanks for listening.